Hello sir, I am Nitin. I am going to discuss something about ECOS. The Embedded Configurable Operating System ECOS is an open source royalty free real-time OS intended for embedded applications. The system is targeted at high performance small embedded systems. For each system, an embedded form of Linux or other commercial OS would not provide the streamlined software required. Next, I'll discuss about ECOS configuration tool. The ECOS configuration tool, which runs on Windows or Linux, is used to configure an ECOS package to run on a targeted embedded system. The complete ECOS package is structured hierarchically, making it easy using the configuration tool to assemble a target configuration. At a top level, ECOS consists of a number of components, and the configuration user may select only those components needed for the target applications. The next figure shows about the top level of the ECOS configuration tool as seen by the tool user. Each of the items on the list in the left hand window can be selected or deselected. When an item is highlighted, the lower right hand window provides a description and the upper right hand window provides a link to further documentation plus additional information about the highlighted item. Items on the list can be expanded to provide a finer grained menu of options. In this figure, it illustrates an explanation of the ECOS kernel options. In this figure, note that exception handling has been selected for inclusion, but SMP, symmetric multiprocessing, has been omitted. In general, components and individual options can be selected or omitted. In some cases, individual values can be set. This diagram shows loading an EOS configuration file. This is a typical example of the overall process of creating the binary image to execute in the embedded system. This process is run on a source system such as Windows or Linux platform, and the executable image is destined to execute on a target embedded system such as a sensor in an industrial environment. At the highest software level is the application source code for the particular embedded application. This code is independent of ECOS but makes use of Application Programming Interface API to sit on top of the ECOS software. There may be only one version of the application source code, or there may be variations for different versions of the target embedded platform. In this example, the GNU Make utility is used to selectively determine which pieces of program need to be compiled or recompiled, and issues the commands to recompile them. The GNU Cross Compiler executing on the source platform. then generates the binary executable code for the target embedded platform. The GNU linker links the application code with the code generated by the ECOS configuration tool. This latter set of software includes selected portions of the ECOS uh, kernel plus selected software for the target embedded system. The result can be loaded into the target system. This is the ECOS layered structure, which consists of user application code, standard C library, IO system, device drivers, kernel, and finally the hardware abstraction layer. A key design requirement for ECOS is the portability to different architecture and platforms with minimum effort. To meet this requirement, ECOS consists of the layered set of components. This is the hardware abstraction layer. At the bottom is the hardware abstraction layer. The HAL is the software that presents a consistent API to the upper layers and maps upper layer operations into a specific hardware platform. Thus the HAL is different for each hardware platform. These are the modules of the hardware abstraction layer: architecture, variant, and platform. Firstly, architecture defines the processor family type. This module contains the code necessary for processor startup, interrupt delivery, context switching, and other functionalities specific to the instruction set architecture of the processor family. Next, variant supports the feature of the specific processor in the family. An example of a supported feature is an on-chip module, such as Memory Management Unit (MMU). Next, platform extends the hardware abstraction layer support to tightly coupled peripherals like interrupt controllers and timer devices. This module defines the platform or board that includes the selected processor, architecture, and variant. It includes code for startup, chip selection, configuration, interrupt controllers, and timer devices. Next, I'll be discussing about ECOS kernel design. The ECOS kernel design was designed to satisfy the below objectives. These are the four main objectives in which the main objective of ECOS kernel was designed. Low interrupt latency, low task switching latency, small memory footprint, deterministic behavior. I'll be discussing it individually. Firstly, low interrupt latency. The time it takes to respond to an interrupt and begin executing an ISR. ISR is an interrupt service routine. Low task switching latency. The time it takes from when a thread becomes available to when actual exception begins. Small memory footprint. Memory resources for both program and data are kept to the minimum by allowing all components to configure memory as needed. Finally, deterministic behavior. Throughout all aspects of execution, the kernel performance must be predictable and bounded to meet all real-time application requirements. some functionality that is typically included in the kernel of an OS is not included in the ECOS kernel. These are memory allocation, device driver. This makes for a lean kernel. For example, memory allocation is handled by a separate package. Similarly, each device driver is a separate package. Various packages are combined and configured using the ECOS configuration technology to meet the requirement of the application. This makes for a lean kernel. Next, I'll be discussing about the ECOS IO system. The ECOS IO system is a framework for supporting device drivers. A variety of drivers for a variety of platforms are provided in the ECOS configuration package. These include drivers for serial devices, Ethernet, flash memory interfaces, and various IO interconnects such as PCI, peripheral component interconnect, and USB, universal serial bus. In addition, users can develop their own device drivers. The main principal objective for an IO system is efficiency with no unnecessary software layering or extraneous functionality. Next concept is ECOS scheduler, in which I will be discussing about bitmap scheduler and multi-level queue scheduler. The ECOS kernel can be configured to provide one of two scheduler designs, the bitmap scheduler and the multi-level queue scheduler. The configuration user selects the appropriate scheduler for the environment and the application. The bitmap scheduler provides efficient scheduling for a system with small number of threads that may be active at any point in time. The multi-queue scheduler is appropriate if the number of threads is dynamic, or if it is desirable to have multiple threads at the same priority level. The multi-level scheduler is also needed if time slicing is desired. This is the bitmap scheduler priority levels. A bitmap scheduler supports multiple priority levels, but only one thread can exist at each priority level at any given point of time. Scheduling decisions are quite simple with this scheduler. When a block thread becomes ready to run, it may preempt a thread of lower priority. When a running thread suspends the ready thread with the highest priority is dispatched. A thread can be suspended because it is blocked on a synchronization primitive, because it is interrupted, or because it is relinquishes control. Because there is only one thread at most at each priority level, the scheduler does not have to make a decision as to which thread at a given priority level should be dispatched next. The bitmap scheduler is configured with 8, 16 or 32 priority levels. A simple bitmap is kept of the threads that are ready to execute. The scheduler needs only determine the position of the most significant one bit in the bitmap to make a scheduling decisions. Next is the multi-level queue scheduler priorities. As with the bitmap scheduler, the multi-level queue scheduler supports up to 32 priority levels. The multi-level queue scheduler allows for multiple active threads at each priority level, limited only by system resources. This figure illustrates the nature of multi-level queue scheduler. A data structure represents the number of ready threads at each priority level. When a block thread becomes ready to run, it may preempt a thread of low priority. As with bitmap scheduler, a running thread may be blocked on a synchronization primitive because it is interrupted or because it relinquishes control. When a thread is blocked, the scheduler must first determine if one or more threads at same priority level as the blocked thread is ready. If so, the scheduler chooses the one at the front of the queue. Otherwise, the scheduler looks for the next high priority level with one or more ready threads and dispatches one of these threads. In addition, the multi-level queue scheduler can be configured for time slicing. Thus, if a thread is running and there is one or more ready threads at the same priority level, the scheduler will suspend the running thread after one time slice and choose the next thread in the queue at the priority level. This is a round-robin policy within one priority level. Not all applications require time slicing. Next is the ECOS thread synchronization. Firstly, I will discuss with the classic mechanisms. The ECOS kernel can be configured to include one or more of 6 different thread synchronization mechanisms. These include the classic synchronization mechanisms, mutexes, semaphores, and condition variables. In addition, ECOS supports 2 synchronization communication mechanisms that are common in real-time systems, namely event flags and mailboxes. Finally, the ECOS kernel supports spin locks, which are useful in SMT, Symantec multiprocessing systems. Mutex. A mutex is used to enforce mutually exclusive access to a resource, allowing only one thread at a time to gain access. The mutex has only 2 states, lock state and the unlock state. This is similar to a binary semaphore. When a mutex is locked by one thread, any other thread attempting to lock the mutex is blocked. When the mutex is unlocked, then one of the threads blocked on this mutex is unblocked and allowed to lock the mutex and gain access to the resources. The mutex differs from a binary semaphore in 2 respects. First, the thread that locks the mutex must be the one to unlock it. In contrast, it is possible for one thread to lock a binary semaphore and for another to unlock it. The other difference is that a mutex provides protection against priority inversion, whereas a semaphore does not provide it. Next is the condition variables. A condition variable is used to block a thread until a particular condition is true. Condition variables are used with mutexes to allow multiple threads to access shared data. These are the basic commands of mutexes and condition variables. Firstly, cyg underscore cynd underscore wait. This command causes the current thread to wait on the specified condition variable and simultaneously unlocks the mutex attached to the condition variable. Next is cyg underscore cond underscore signal. Wakes up one of the threads waiting on this condition variable, causing that thread to become the owner of the mutex. Next is cyg underscore cond underscore broadcast. Wakes up all the threads waiting on this condition variable. Each thread that was waiting on the condition variable becomes the owner of the mutex when it runs. Thank you.